we have the situation where we have two masses, M1 and M2, with radii R1 and radius R2. Okay, well, at this point their centers are separated by the radius of this one plus the radius of this one. Now, if we want to separate these, okay, separate along a straight line. So you just kind of pull this one along a straight line, kind of leave this one where it is, or, yeah, you can pull them apart, doesn't really matter. You're just separating them, okay? When the separation is R, okay, and R being the distance between the centers, then at this point, this one will be pulled back by gravitation with a force, big G, M1, M2 over R squared, right? Now, if you partition the separation, then you could say that, well, okay, at this point the separation is approximately R sub I. We'll make that R sub I star, and that will be the typical force for that particular interval. Okay, subinterval. So that'll be the force F sub I. The work done will be approximately equal to G M1 M2 over R I star squared times delta R sub I. Then the total work in separating will be an integral of this expression, but in the case of an integral, we're going to have G M1 M2 over R squared dr. The Ri squared gets squeezed into just a continuous R as we take the limit as the widths of these intervals approach 0. And the delta R sub I becomes a dr. By magic, by Riemann sums, by stuff you should understand from first semester calculus, but in physics we wave our hands a lot. So this gives us this. Now, total work from where to where? Total work from here to there. In this case, here is separation R1 plus R2, and there is infinity. Okay, so that would be the integral then of G M1 M2 over R squared dr, separation R1 plus R2 to separation infinity. And this will be equal and opposite the potential energy change from here to there. Potential energy equals 0 at infinity, then the change in potential energy, well, you do this integral, you get the negative of the change in potential energy, so you just do the negative of that, then you find that the potential energy change from here to infinity is big G M1 M2 over R1 plus R2. So that the potential energy here is going to be negative of that. Now you need to fill in the details, but the potential energy here will then be G M1, M2 over R1 plus R2 with a negative. You can, and you need to wrestle out why that's negative, okay? And I'll tell you, it's negative because potential energy keeps increasing as you go to infinity, and it keeps increasing towards zero. You can't increase towards zero unless you're negative. Okay, now, we have this. There's potential energy here. And there's a question about, well, where would you have to go so the potential energy is half of that? Write that out carefully. Write it as an equation. Figure out what the potential energy would be at distance r. Fairly easy to do. And then potential energy at distance r, you'd integrate from here to there, but here would be r to infinity. That'd be your integral. That'd be the negative change of potential energy, etc. You want to work that out.